Hello, in this video we're going to look at Welch's approximation, and that is an approximation for a confidence interval for the difference of two population means. So that's our goal, is to construct a confidence interval for the difference of two independent populations of means. And in a video just before this one, we showed that this quantity here is asymptotically normal, and with no assumptions about the population distributions for X and Y. But for this distribution, for this derivation, we need to assume that each populations are independent and normally distributed. Okay, so here, let's move on. So now let's let Z be the numerator here, but divided by the variance of X bar minus Y bar. So the standard deviation. And then this, of course, goes to standard normal. And we have W, we're going to be this quantity, which is sort of like this in the numerator, and then like this in the denominator. So the T can be constructed like this. T is equal to Z over the square root of W. And what is so ingenious by Welch is the numerator, of course, is a standard normal. And if the denominator were a chi-squared divided by its degrees of freedom, well, this would be a T distribution. But this is clearly not a chi-squared divided by its degrees of freedom. But Welch noticed that it's pretty darn close. So let's find out what it's close to. And then this would be an approximate T distribution. And so that's the steps we're going to take in this video. Okay, so the first assumption, actually I started here, and just before I did the video, I'm like, nowhere we have to assume that the populations are normal and independent, so I had to put in a step 0. But W is not a chi-squared divided by degrees of freedom. That's pretty obvious. So Welch noted that W does approximate a chi-squared divided by its degrees of freedom. So what he wanted to do was, let's approximate, let's find a chi-squared divided by its degrees of freedom that's really close to W. Then this will be an approximate T distribution. And that's the steps that he took. So we're going to rewrite W like this. Okay. And it can be rewritten as in this. So it's lambda, times U, where U is this quantity divided by n minus 1. And then 1 minus lambda V over n minus 1. And we do that because these are chi-square distributions, U and V are. And they're chi-squares divided by their respective degrees of freedom. Now this is a constant, for a given M and N in the population variances. So we note that U and V are chi-square distributions. So that's the sample variances, and lambda is a constant. So what we want to do is we want to match the moments of these two quantities. So W is what we have, and this is what we'd like. So we're going to take the first moment and the second moment, and then equate them to the first moment and second moment of W. So here we do it for the first moment. So we take a chi-square random variable, whatever it is, divide it by its degrees of freedom, and then the expected value is, well, we take out the constant, and the expected value of a chi-square is the degrees of freedom, so then this is 1. So now let's do that with W, and the way we rewrote W, we can take, it's a linear operator, so we can take it in. This is constant, and then this is a chi-squared with m minus 1 degrees of freedom, and then this is a chi-squared with n minus 1 degrees of freedom. So those cancel, and we're left with lambda plus 1 minus lambda, which is 1. So actually the first moments agree. So the first moment acts like a chi-squared with divided by its degrees of freedom. Now let's take the variance of both sides. So let's do the chi-square first. So to take the variance, we have to square the constant, bring it out front. And then the variance of a chi-squared is 2 times the degrees of freedom. So one of those this cancels one of those, leaving 2 divided by v, which is the degrees of freedom, or nu, or whatever the Greek letter is. Now let's look at the variance of w. So we square the constants out front, and we're left with this, plus we square the constant and this, and they're independent, so there's no covariance. The variance of a chi-squared is 2 times the degrees of freedom, 2 times the degrees of freedom. So one of those cancels here, one of those cancels here. The 2 can be brought out front, and we're left with this. Now, we need to equate this quantity and this quantity. So I brought the 2 out because we can essentially make that go away and have 1 over nu, or v, equal to this. And that's what we do. So if we solve for v, and then that's our degrees of freedom for our t distribution, and then that ratio approximates the t distribution very closely. So to solve this, then t is approximately t degrees of freedom with this degrees of freedom. So now we need to solve it. So we take the reciprocal to get v, and then 1 over this quantity. And then remember we replace what we denoted lambda to be, and then you solve and you get this. And that's it. And that's actually the Welch's approximation for the degrees of freedom needed. But one downside here, these are population variances, and we don't know those. So we have to approximate them. So we have to approximate the degrees of freedom with the sample variances. And so we plug that in, and then we get the approximate degrees of freedom. Then our t distribution, see if I can flash this, that we got in the front. So this is approximately a t distribution. So the probability that t is between these 2 cutoffs with the appropriate degrees of freedoms is approximately 1 minus alpha. Then you can solve for the difference of the population means, and you come up with this confidence interval, and it's a 1 minus alpha % confidence interval. Anyway, and that's it. And that's the Welch's approximation to a 90 or a confidence interval for the difference of 2 independent means. Yep, and hope you enjoyed it. I sure did. Please like it and subscribe so you don't miss the next one. The next video, we're going to look at the exact confidence interval for the difference of 2 population means. And there you have to assume that the population variances are equal. Welch's, you don't have to assume that the variances are equal. So then the video after my next one will be an R simulation comparing the 2 different approaches for finding a confidence interval. So that's all I have. Talk to you later. Bye.